Hello everyone, welcome to our channel. In this video, we are going to solve a problem which came in the year 2017 in JAM Biotechnology paper. Here the question is, the average energy of a diatomic gaseous molecule at temperature T is 5 by 2 kBT, where Kb is Boltzmann constant. The average energy of this molecule per degree of freedom is option A, half kBT, option B, 2 by 3 kBT, option C, kBT, option D, 3 by 2 kBT. Okay, so to solve this problem, we first need to know what is the number of degrees of freedom of a diatomic gaseous molecule. Okay, so if we consider monoatomic gaseous molecule, that means a molecule which have only one atom, which is made of only one atom. Okay, so for a monoatomic gaseous molecule, how many degrees of freedoms are there of it? If it is the x-axis, it is the y-axis, and it is the z-axis, then this molecule can move along this direction, right? Along this direction, this axis, and along this axis, right? That is along x direction, along y direction, and along z direction. That means monoatomic gaseous molecule have 3 degrees of freedom. Okay, 3 degrees of freedom, and these 3 degrees of freedoms are translational degrees of freedom. 3 translational degrees of freedom. Okay. Now, if we talk about diatomic gaseous molecule, okay, degrees of freedom is the number of free motions. Okay, number of freely motions. Okay, so in case of diatomic gaseous molecules, let us first draw the two gas molecules. Okay, and they are connected by this bond, right? A bond is there in between these two atoms. Diatomic molecules mean 2 atoms. One molecule formed with 2 atoms. So there is a bond between these 2 atoms. Now, how many degrees of freedom is possible for these 2 atoms of the molecule? See, if we go by the formula for calculating degrees of freedom, then see, first of all, for the first atom there are 3 degrees of freedom, and for the second atom there is 3 degrees of freedom independently, right? But there is a bond between them. That means the total number of degrees of freedom is 3n minus r. Okay, here n is the number of atoms, here n is 2, so 3n minus r. R is the restriction or the number of bonds. Okay, so the formula is F equal 3n minus r. Now, in case of diatomic molecule, n is 2 here, and r is 1 because only one bond is there, right? So F equal 3 times 2 minus 1, that is 6 minus 1 equal 5. Okay, now let us just analyze that what are these 5 degrees of freedom. Okay, see this atom, the first atom here, this have, as I said, that this can have 3 translational motion, and the second atom has 3 translational motion if they were not bound. That is, this bond, if the bond is not present, right? But when the bond is present, it can have these 3 translational motions with 2 rotational motions, right? How? In this manner, okay, that is in this plane, when this is our x-axis, okay, then it can rotate in this plane. Now it can rotate in this plane also, here in this direction, that is along z-axis. But in which direction it cannot rotate is along y-axis. Along y-axis it cannot rotate. So it has 3 translational motions plus 2 rotational motions. But here one thing you need to know, that is, we can say that this 5 degrees of freedom is enough, or is present for diatomic gaseous molecules only when the temperature is low, for low temperature. Okay, if temperature is high, there is 2 more degrees of freedom is possible, that is 2 vibrational motions, one for the first atom and second for the second atom. Okay, so there are actually 7 degrees of freedom. 7 degrees of freedom. Okay, but since we are talking about low or normal temperature, so here we should take F, or the number of degrees of freedom, as 5. Okay, F equals 5. So here average energy of the molecule per degree of freedom is, take this 5 by 2 kBT, 5 by 2 kBT divided by 5. Okay, and that is equal half kBT. Okay, half kBT. So this is our average energy of the molecule per degree of freedom, and that is option A, half kBT. So here you need to remember, when you should take 5 as the number of degrees of freedom, and when you need to take 7 as the number of degrees of freedom. At lower temperatures, that is normal temperatures, that is up to almost 1000 Kelvin temperature, you can take F as 5. Above that, the degrees of freedom, that is the 2 vibrational motions are possible. So the number of degrees of freedom then is 7, and below 100 Kelvin, actually almost 100 Kelvin, below 100 Kelvin, only 3 translational motions are possible. These 2 rotational and 2 vibrational motions are not possible. Okay, so you need to understand which temperature, or when you should degrees of freedom you need to consider. Okay, here you need to consider the normal temperature. At normal temperature, that is, the number of degrees of freedom is 5 here. Okay, so I hope I could successfully explain this solution to you. If you have any doubt regarding this solution, you can tell me in the comment section. If you like this video, please click on the like button, share this video with your friends, and don't forget to subscribe our channel. Ta-da!